Right, I'm now going to do another harder integral, which some students and scholars find a little troublesome. And the integral is the integral of 1 over 1 plus x to the fourth dx. Now, the denominator here can be factorized, but we will end up with some surd expressions which make the subsequent work quite messy. So I've devised another method for doing it by letting x equal e to the power u, so that dx equals e to the u du, and the integral will transform to the integral of e to the u du over 1 plus e to the power 4u. The next step, I've multiplied the numerator and the denominator by e to the power minus 2u to get the integral e to the minus u du over e to the minus 2u plus e to the power 2u. So, and that transforms to 1/2 cosh u minus sinh u over cosh 2u, which in turn can be split up as 1/2 cosh u du over 2 sinh squared u plus 1 minus 1/2 sinh u du over 2 cosh squared u minus 1. The denominators in both of those expressions there are actually both equal to cosh 2u, and the reason I've put them slightly different will become apparent in the next step. I've numbered these two integrals as 1 and 2, so I'll deal with 1 first. We have to make another substitution, so let p equal sinh u, so that dp is cosh u du, and the integral transforms to 1/2 integral dp over 2p squared plus 1, which is a standard integral, and that will be 1 over 2 root 2 tan inverse p root 2, which, going back to the old variable, will be 1 over 2 root 2 tan inverse sinh u times root 2, and then because sinh u is e to the u minus e to the minus u over 2, that expression becomes 1 over 2 root 2 tan inverse e to the u minus e to the minus u, all times root 2, and then divided by 2. And that then gives us the next step, which is this one here, which is 1 over 2 root 2 tan inverse x minus 1 upon x over root 2, which equals 1 over 2 root 2 tan inverse x squared minus 1 over x root 2. So that's as far as we've got there. I'll say a word about this one at the end. So, for the second one, we let q equal cosh u, so dq is sinh u du, and the integral transforms to minus 1/2 dq over 2q squared minus 1 minus 1/2 dq, and we factorize the bottom as q root 2 plus 1 and q root 2 minus 1, and using partial fractions we get the next step, which is minus 1 over 4 root 2 integral square root of 2 over q root 2 minus 1 minus square root of 2 over q root 2 plus 1, which are easily integrated, and what that results in is 1 over 4 root 2 q root 2 plus 1 over q root 2 minus 1, and then substituting for q, going back to the old variable, that'll be 1 over 4 root 2 log to base c square root of 2 cosh u plus 1 over square root of 2 cosh u minus 1, and using the fact that cosh u equals e to the u plus e to the minus u over 2, and that e to the u is equal to x, this soon becomes the final result here, 1 over 4 root 2 log to base e x squared plus x root 2 plus 1 over x squared minus x root 2 plus 1. And then putting all our results together, we get finally the integral of dx over 1 plus x to the fourth is equal to 1 over 4 root 2 log to base c x squared plus x root 2 plus 1 over x squared minus x root 2 plus 1 over 2 root 2 tan inverse x squared minus 1 over x root 2 plus c. Now, I've included the constant here for a good reason. It's because the tan inverse part can also take the form tan inverse x root 2 over 1 minus x squared. You'll find if you differentiate those two expressions, you'll end up at the same result. Okay, so that means the two tan inverse expressions will differ. In fact, what they differ by is pi upon 2 for all values of x. And this difference can easily be transferred into the constant c. Okay, so that ends that little bit, but I've just written down to follow in the next episode. You've got two integrals, x squared over 1 plus x to the fourth, and integral of square root of tan theta d theta. And these are related to the one we've just done, but I'll do that when I've recovered. Thank you for listening.